Hi there, everyone. This is the Practical Actuary channel, and we're diving into a series called RAG-Based Knowledge AI Agent. And this video is part one of two, where essentially give an overview of the concepts. Part two is where we go into the tutorial of building an IFRS 17 knowledge AI agent. But for now, let's go over the concepts. Okay, let's dive in. Cool. So what is RAG? Where does it come from? So RAG actually stands for Retrieval-Augmented Generation. And this term was first introduced back in 2020 by a number of authors, Patrick Lewis and the others from the Facebook AI research team. And I suppose this is the earliest where we can find the term Retrieval-Augmented Generation. Of course, there are other, call it retrieval methods before this paper, but essentially they came up with the term. But RAG is, so think of it this way, right? So you have an LLM, a large language model, which was trained on a given set of, data. Wikipedia, some internet text, it's trained on that data. And some of that knowledge is then embedded in its parameters. It's sort of stored in its parameters in an implicit way. And we call that a parametric, parametric memory, right? Because you have the knowledge that is stored within the parameters of the LLM. Now, what RAG introduces is that you have knowledge that is non-parametric, that sits outside of the parameters of the LLM. So think of it this way: you have a database, right? That's external to the LLM, and that database consists of data, information. And Retrieval-Augmented Generation is a technique where, based on the query, retrieves the relevant knowledge, the relevant data to the query, and essentially then augments sort of the input into the LLM and then outputs, whatever answer or response to that query, a given set of data that it retrieves from an external database. So that is, in a nutshell, what RAG is. So it's a technique that enables LLMs to retrieve and incorporate new information, right? That's not necessarily trained on, and it modifies the interaction, the output of the LLM, not solely based on just the query, but it's the query plus the retrieved information. So that's in a nutshell what RAG is. But let me just go into an example of a RAG application to sort of then highlight the steps involved in a RAG application. So firstly, you have a set of documents, a set of data, and this data will go through some processing steps. So it gets divided into chunks. So whether it's paragraphs, pages, text, let's just say of 500 words, length, and those chunks could overlap each other, but it's large documents that are then broken down into chunks, and these chunks then go through a document embedding model. Sometimes you might see like a sentence embedding model or a text embedding model, but essentially it takes these chunks, goes through the model, and it outputs a dense vector. Where this dense vector is a representation, a semantic representation of that text. It captures the meaning of that text into a dense vector, right? So it's a numerical representation of that text. And these vectors are then stored in a vector database. So it's indexed. So you have the text, the document, and you have the vector, and both of them are then stored in a vector database. So if you were to search for a vector, you can then pull the corresponding document with that vector. So that's the data that's stored externally outside the LLM, and it's stored within a vector database. And essentially, you need a document embedding model, and you need sort of some infrastructure that data structures, a database that can store this information. Now, you have that. And now a user has a query, right? So this is a query to an LLM, and it might ask, what is X? So the first thing to do is pass that through the document embedding model, so that it then embeds that query into a vector. So you have a numerical representation of that query, and that query will then go through a similarity search, or semantic search, right? Where essentially it looks into the database, the vector database, which contains the stored documents, and it finds relevant documents, where those relevant documents would be those documents or those vectors that are closer to the query vector, right? So it's think of it from a Euclidean space perspective, a vector that is close to the embedded query, or could be a cosine similarity, so it's more or less the direction of the vector. So yeah, you then pull those documents that are quite close to the query, and it returns a set of vectors or a set of associated stored documents, document chunks, and those become your retrieved document chunks, right? So you have the text that is relevant to the query. And you take that text and you take the query and you do some prompt engineering. So there's a prompt template where you essentially then augment that query to say, hey, look, here's the retrieved document chunks, treat this as the context. Here's the user query. Now respond to the user query given the retrieved document chunks. So the contents could be document Y, and the query is what is X, and the LLM then takes that as an input and outputs, well, X is Y. So that's the generation component. So this is in a nutshell an example. There are many examples of RAG application, but this is a simple example of a RAG application, and this essentially gives an overview of how it actually works. So you need a vector database that stores some text, which goes through some embedding model, and any queries will then go through that same embedding model, and then there's some similarity or semantic search, and that augments the query and goes through an LLM. Okay, so let's just zoom into the document embedding model. What is that? What does that look like? So first, I just want to show a naive model, just to highlight the high-level principles of a document embedding model. This obviously assumes some knowledge of word embeddings, word embedding models. Things like glove or word to vec. There are various word embedding models that are out there. But let's just say you have a document. It's a simple text with 4 words that says actuaries are problem solvers. And this will go through some tokenizer. The tokenizer will say, okay, this is essentially an index of the word from a dictionary or corpus. And that tokenizer then looks up the associate, the corresponding vector, right? So it's the word embedding. And this could be like a word to vec, or it could be a cloud model, it could be a BERT or some other transformation model. But it's just a model that produces a dense vector space that is a semantic representation or numerical representation of the word, right? Which has some semantic meaning in that vector space. Obviously, there are different types of word embedding models. Transformer models usually have a contextualized meaning. So the output, the vectors, would essentially represent a contextualized meaning of the word. Whereas in non-transformer models, such as your word-to-vec, wouldn't necessarily have a contextualized meaning of the word, right? So an example would be an apple. Apple on its own, will have some vector. But if an apple is surrounded by words like I bought an iPhone, an Apple iPhone, right? So that the word apple suddenly changes, right? The meaning of the word changes. Versus I ate an apple, for breakfast. Apple is my favorite fruit. It has a different meaning. So transformer models is able to sort of transform that vector, right, into another vector that will contain that meaning, a contextualized meaning. And this is not necessarily true for like word-to-vec models, whether it is surrounded by like iPhone or fruit, it doesn't change. It's the same vector. So that's the difference between transformer-based models and other models such as word-to-vec. But nonetheless, each word will have a corresponding vector, right? So it's a word embedding vector. And so we have 4 vectors, and they could be of different length, right? So it could be 500 length, so that's the dimension of the vector. It really doesn't matter, but you have 4 vectors, each representing actuaries are problem solvers. And this is not really good for sentence embedding, because a sentence can contain a variable number of words. And I think that's a problem that needs to be solved. You need a vector of fixed size length to represent the meaning of a text, right? Which could be 10 words long, it could be 200 words long. So how do you do that? You need a pooling function, a pooling step, and this could be, as an example, taking an average of the vectors, right? So you just take the average of the 4 vectors, and essentially then you have one vector. And this one vector is supposed to represent the sentence actuaries are problem solvers. Now, there are issues with this approach. And the first issue is that they tend to be anisotropic, maybe I'm pronouncing that fine, in let's just say Euclidean space. And what that means is that you have vectors that are generally pointing in the same direction, right? So they've got a very small space, or that small space is shared by like all the vectors, right? And it becomes very hard to differentiate one vector from the other. So if you're using cosine similarity between 2 vectors, that can generally be high. And it can be high for even like contrasting documents or unrelated documents. And you don't want that, right? So you want contrasting documents to have vectors that I suppose go in different directions, and not necessarily be close together or go in the same direction. So that's the first problem. The second problem is the models are trained to, it's a word embedding model. It's not a sentence embedding model. So it, an average doesn't necessarily capture the semantic meaning of the sentence. You could have 4 words with a different order that could mean something different. So it's a very naive model, right? So it works, but it works poorly because of these 2 issues. Is first, in that space, it's very difficult to contrast two documents. And second, the model isn't really trained to capture semantic meaning. It's trained to capture the word meaning. And depending on the model, the contextualized word meaning as well. So yeah, this is a naive model. So what do you do then? Some papers, so you might have heard of sentence BERT, or even that paper that we just saw right now. They use something called contrastive learning. And what that is you have a word embedding model. So it's a pre-trained word embedding model, so like a BERT model. And you essentially have, two, call it like a Siamese network. You have sentence A and sentence B, that will go through the same pre-trained model. And then you have pooling, so it's an average of the word. And then you have essentially the vector, the sentence embedding vector. And you then calculate, the cosine similarity or whatever similarity function. And you apply contrastive loss function on top of that. And you train the model so that, it then back propagates and the parameters are sort of updated. And that update will then, I suppose the loss will reduce from contrastive loss function perspective, such that at the end of the training, you get a sentence embedding model, because it is learning how to differentiate or apply some contrast between two sentences. So, one example of a loss function is simple mean squared error. So you have, let's just say you have two vectors and they could be a positive pair, which means these two sentences actually mean the same thing. So, for example, is I had fun today, or today I had an awesome day, right? It's different words, but they have the same meaning. You enjoyed the day. That is the meaning, right? So it's a positive pair, and ideally is that you want those two vectors to be very close together, to point in the same direction, and so the cosine similarity of that should be 1, right? So obviously, those sentences will go through these two. So you have vector A, vector B will have a cosine similarity. If that is close to 1, then yeah, your loss is quite low, right? But if it's far from 1, let's just say it's -1, then you have a huge loss, right? And then the model then updates the parameters to ensure that those two vectors, to be close together. And the opposite is true if you have a negative pair. And those negative pair could be some like opposite sentences or could be unrelated sentences. So that's essentially one example of a loss function. Another example is info noise contrastive estimation loss. So this one is a different approach. So you have, let's just say a sentence. You have a number of sentences, right? And two of them could be a positive pair, but you also just throw in negative sentences or unrelated sentences, unrelated documents. And you apply a contrastive loss to the set of documents. And this loss function enables you to do that, right? So it's multiple documents. Where you just want to recognize that these two pairs, two sentences that are quite related, they're positive pair, but then the rest are unrelated. So that's the numerator here, which is essentially the plus there means that it's a positive pair between the query and the document. So the S is a similarity function. Let me just put on a laser here. Okay, so this S here is a similarity function, and it applies similarity function to a query and a document. And the positive means that it's a positive pair. And in the denominator, so you have that same query and document, which is a positive pair. And then you have the negative pairs, so the query and other unrelated documents, right? So you sum them up. So this could be one loss function. And yeah, so you essentially want to minimize this function. And training the model, then you have, remember, it's the same model, the same set of parameters, so they share the same parameters. So you then just take that block where you can then input a sentence, and that pre-trained wording embedding is then, because the parameters are updated, it's now an embedding model that goes through a pooling function that outputs a vector embedding that is now trained to represent the meaning of the sentence. And vectors are now more isotropic, so they go in various directions, and they're well suited for document similarity search. So this is a technique that they apply, which performs better than the naive model that I just went through. So yeah, hopefully, you now understand text embedding models or document embedding models or sentence embedding models. So these are terms that tend to be exchanged. Yeah, so I mean, why not just use pre-trained or fine-tuned LLMs for knowledge-based tasks, right? Because I mean, LLM can be argued to be a form of parametric memory, as I explained before, right? So the data or the information is retrieved through its generation of the tokens, right? Given a set of tokens, so it's within it. So you have a given set of tokens, so that's your query, and that's the way of retrieving some information within the LLM, such that the output, the generated output, is the retrieved information. So LLMs can be viewed that way, right? However, they tend to be static knowledge based, right? So LLM's implicit knowledge is based on training data at a point in time. So it's very static. There could be new information after that point in time, and its parameters won't reflect that new information. Second problem is that it's a limited knowledge base, right? So LLMs may only be trained on a limited training data that is not necessarily appropriate for your own specific knowledge task. So what do I mean by this? So an LLM could be trained on, let's just say, Wikipedia database, right? But that Wikipedia database may not necessarily contain sufficient data for some specialist or specific knowledge task, right? That you might probably find elsewhere that is not in the Wikipedia database, as an example. The third problem is hallucinations. So LLMs generate responses that are based on patterns in the training data, right? So anything that it generates is kind of reflective of the patterns that it identifies while it was training. And what this means is that you can't guarantee factual information being generated. It can generate anything as long as the patterns are, somewhat similar. And this is what we call hallucination, where you can't really guarantee that the LLM will output factual information. The fourth issue is limited parameterization. So LLM parameters may not be large enough, right? So a 1 billion parameter LLM is very different to a 14 billion parameter LLM, which is very different to a 70 billion parameter, and there are obviously larger models that are out there. You need enough parameters to store data. 1 billion parameter model may not store sufficient data, right? Store sufficient knowledge. It also depends on how they're structured. how well they adequately structured. So the parameters themselves, whether that is a mixture of experts or some other transformer architecture, right? Well, it really depends on the architecture. Or sometimes they're not really trained well enough to store sufficient knowledge data, right? So there might be a cutoff point in terms of the training data. So it's really the limitation of parameterization. So these are the issues that I suppose limits the use of LLMs for like knowledge-intensive tasks, and that's why RAG-based LLMs, RAG-based knowledge AI agents tend to perform better. But it doesn't mean that they're perfect. One more. LLMs are also expensive to update. So you almost have to like fine tune them every time new information comes in. And this is computationally expensive. Okay, so what are the downsides of RAG? So there's a dependency on external data quality, right? So this is essentially your documents that you are storing, right? So that you're passing through that embedding model and then putting it in a vector database. That document that you're putting it in that vector database, might be outdated, might be incorrect, might be irrelevant, might be biased. There might be some issues with that data. I mean, if you're storing rubbish data, it's going to retrieve rubbish data, and this might mislead the model in its responses. Another issue with RAG is the risk of irrelevant or mismatch retrieval. The documents that it retrieves based on search queries depends on how well the contrastive learning, is sort of implemented, or the model is trained on the contrastive learning, and the quality of your training data, right, to ensure that contrastive learning is very good. So that contrastive learning might be imperfect. So as a result, you might find two irrelevant documents close together in the vector space, and RAG will essentially then might retrieve that document that is really irrelevant. So it doesn't mean that it's perfect. It's just that you do have these cases, right? You do have these errors where generally, yes, it does well, but there could be some instances where you might retrieve irrelevant documents. The third is limited reasoning and contextual understanding. So think of it this way, right? You've got a document, like let's just say 20-page document. And as you read through the 20-page document, you do have a hierarchical view of that document. It's got content, it's got sections, how they speak with one another. This might reference some concept explained earlier on. So as you read as a human being, you sort of have that contextual understanding of the entire document. But now when you're retrieving text, you are sort of then retrieving a chunk, and you're missing sort of the context of that chunk. And it doesn't really have that hierarchical understanding, contextual understanding of the retrieved document. So, and it's unable to logically, or to have some logical reasoning on the extracted documents, on the retrieved documents. So this is the limitation. There are obviously other techniques to overcome that. So like graph RAG, which essentially then tries to limit this downside of RAG. The other issue is computational costs and infrastructure needs, right? So you have an LLM, and you need some infrastructure to host that LLM, GPUs, etc. But for RAG, because you're storing information in a vector database, you need a very robust vector database that is able to index the vectors, right, and retrieve it with speed, with reliability. So there's an infrastructure needs associated with having that external knowledge stored in the database. So yeah, that's, and that might attract more costs in terms of ensuring that there are people that is, ensuring maintenance of that vector database, there's updates, ensure that it's always up and running, there's availability, etc., etc. So that's one of the downsides. So that's essentially it for now in terms of part one, where I've sort of taken you through an overview of the concept. So hopefully, you now have a better understanding of RAG-based LLMs or RAG-based AI agents. But yeah, do look out for part two. It is a tutorial on building IFRS 17 knowledge AI agent. That will be a fun tutorial. I promise you. As boring as IFRS 17 is, I think this will be a fun tutorial. Cool beans then. Check you later.